Thanks for having me back. Um, the the series name has changed slightly because I think as I kind of get the material together and actually create these presentations, only then does kind of a logical structure sort of present itself. And so remember at the end of the last lecture, I asked if it would be appropriate for me to extend this into a 4 seminar series rather than 3. Rabbit was kind enough to let me do that. And so the structure has changed. It used to be these 3 subheadings. The first 2 have really turned out to be both introductions to the seminal archetype, where the first one was really just establishing nomenclature and conventions, and the second one was discussing portfolio compositions in n dimensions. So these are both completed. And the one that we're going to be doing today, I've called concentrated prototypes, virtual tokens and augmented hyperbolas. And this is going to be handling both 2-dimensional and n-dimensional spaces, which means that the 4th slot is still going to be the exotic bonding curve types. And I'm going to put in some additional theory that kind of buttresses things that you've already seen. So we'll be returning to some of the material presented in the last 3 lectures that I said that I would eventually return to. Things like an AMM as a depth book or as a liquidity book, and how to use fees, and then also using different types of invariant functions that give you different types of slippage profiles or price impact profiles, and we'll discuss exactly what those words mean in that one as well. So today, really, just focusing on concentrated liquidity prototypes. But I think I need to correct a couple of things that I said in the last lecture. These are all very, very minor. The first one is that on this slide, I had neglected to substitute out some of the old syntax for the new syntax. So this is, this Rx should have been Ri, this Ry should have been Rj, and so on. So nothing too dramatic. And then I caught this while I was presenting in one of the homework solutions. This is the one where you're removing liquidity in 2 tokens simultaneously. This should be a minus sign. So there was a sign inversion all the way through this solution, and I apologize for that. And so you can see I'm just listing out exactly where those sign inversions occurred on the slides, and listing the recording play times in case anyone needs to, or anyone has been going through trying to perform some of this work themselves and ended up getting stuck. So that sign inversion was there, and that's basically the end of the mistakes. Let me know if there are any others that I am fallible, and I would be very happy to address these things as they come up. Okay, so moving on. With today's lecture, I have constructed a cheat sheet for essentially all of the material that we have discussed up until this point. This includes all of the reserve invariant components, the add and remove liquidity components, the trading components, and the exchange rate equilibration. I've noticed, both Rabbit and Octopus have sent me some initial attempts at completing some of the homework from last week. And I noticed in some of their notes that they're saying that they need to have a look into the balancer white paper in order to get the in given out and out given in swap equations. And I just wanted to point out that these trade by source and trade by target equations are those equations, right? There is actually no difference between balancer and Bancor V1. And so, I try to not ask any questions that I haven't already prepared you for. There should be no need to find any other material somewhere else. Obviously, you can do that. I encourage you to do that, but don't feel like there's any any prerequisite knowledge to these lectures other than a fairly developed command over algebra and geometry to understand them. Okay, so in that vein, let's have a look at this homework assignment. which was that, I presented a situation where we create a liquidity pool under a certain state, and then we allow the oracle prices to change. And then I showed you that it's possible to create a series of swaps that will bring the entire portfolio into agreement with whatever that oracle price is. And so the question was then, if we allow the oracle price to change a second time, which here I've let everything equal $1, then the question is, how can we rebalance it again? And so this is that price equilibration equation that I presented in the last lecture. And the first thing that you should realize is that this constant term C is calculable immediately, right? If you've got all of the reserve balances and all of the reserve ratios, then it's possible to get this value out relatively easily. I generate most of my numbers to 100 decimal places just because Python allows me to do that. But obviously you'll get some rounding errors if you're using fewer significant places. I think the IEEE standard is only 15 or 18 significant figures. And so just know that your accuracy is going to be no better than essentially what you would get on a fixed point system on Ethereum, for example. So if you've got the accuracy, why not use it? And so I'm just reporting all of the digits that I have available. Once we get to that position, we need to start sort of moving through the rest of this equation. PI and PK are obviously referring to the oracle prices. And I think now is a good time to revisit what the price convention is for the specific equation. Remember that the price of any token, let's say that this was ETH, we need to invert the oracle price in order to get the amount of ETH per dollar rather than dollars per ETH. Now, in this particular case, and this is the reason why I set them all to $1, is that it doesn't matter, right? Because 1 over 1 is the same as just 1 itself. But had I chosen any oracle price other than the number 1, then this inversion might have messed you up. So just remember that. This is very important for this specific equation. Obviously, if you wanted to, you could report it in the familiar dollars per token syntax. And that would mean that this PI and PK is just the inverse of itself. So it would be RIC over PI and RK over PK. But you get some other weird artifacts when you're trying to use this in other contexts. So it's the way that I quote these price conventions is deliberate. And so just, it's better to adhere to them while you're sort of dealing with the material that I present. And if you decide that you want to adopt the other convention, you become aware of these kinds of edge cases, then that's fine. So the oracle price figured out. Now it's just a matter of dealing with these reserve ratios, which of course are all listed here. So not too difficult. And that means that we can at least start stepping through this part of the equation. So we've already got C. We've got the oracle prices for all of the tokens in the system, and we've got all their reserve weights. So just multiplying that value that we had before by this new value that we've calculated gives us this new constant. And then once we've got that, we can actually just start stepping through each row of the table and calculating what the reserve balance should be at these oracle prices. So here, if we've got the A token, then XPA is going to be equal to, P of A, which is $1, or the inverse of $1 rather, times 0.2 times whatever this constant is. And we just do that for the rest of the table in order to generate all of these reserve balances. So if you got this far, then I think that that's a pretty satisfactory result, right? I've given you a new equation. It's got a bunch of different parameters in there that you need to become familiar with. So if you got to just a balanced state for this table, I'd say that that's good, at least half marks or something like that. But remember, the question is actually, how do you rebalance the pool, right? What are the arbitrage steps? And there's more than one way that you can answer it, because I haven't actually given you any details about specific implementation. So if all we're doing is looking at a state that the pool was and a state that the pool needs to be in, then one of the things that you can do is actually just compare those two states. And if we have a smart contract that allows us to move between states in a multi-token sense, then you can just note that, there's a certain number of tokens going in and a certain number of tokens going out. This, I would say, is, good enough for full marks, right? You're just pointing out that, you need to swap these tokens in these quantities and receive these tokens in these quantities. And now the pool is in a balanced state. However, it is very uncommon. In fact, I'm not sure if there are any examples where the smart contracts actually do allow for swaps by sets. More often than not, the only thing that you can do is swap one token for one other destination token. And this is a much more difficult problem to solve. So here, I have one of these possible solutions. For example, we can start by looking at the XE token and just swap everything that we need and get out, one of these other A tokens. But then notice that after that, I actually then get a second amount of the XA token later on by swapping a different token in. And there are certain things that should be going through your mind right now. Like, okay, if I swapped E for A and then D for B, like, was this necessary? Because now I've got some B here that I now need to put, like, I just took all of this B out of the system and now I'm putting it back into the system in order to get this A out, right? Like, these are, there are certainly efficiency problems with the solution that I've proposed, but it doesn't necessarily mean that there is a more efficient result. So as a sort of food for thought, just a special challenge if you want to do it, I've got this challenge, which is construct a visual proof that for any liquidity pool with n dimensions, that there exists a state where all of the marginal rates agree with the oracle price, and that state can be reached in at most n-1 discrete token to token swaps. This is actually, like, if you start to wrestle with it, it's not too difficult to achieve. There is a very nice visual proof for this. And as a hint, if you start thinking about like a small number of dimensions first, you will then realize that the way that these manifolds build is actually it's trivial to demonstrate this. But the method that I have, you will always generate the solution in at most n-1 swaps. Not all general methods will. So there's actually an infinite number of ways you can rebalance this pool. And that brings me to another question. So I've just answered this first one for you, which is how many arbitrage paths are available. If you include, iterative or sort of like Newton-Raphson sort of approximations that slowly perform a swap and then reanalyze the system, you can do this an infinite number of times. But what if you said that you wanted to do it sort of in bulk? How many arbitrage paths are available by swaps only? And then moving on, what if, as the arbitrageur, the person who is rebalancing this pool, is only allowed to redeem pool tokens, right? Remember in the case that I showed you in the first lecture, that if you've got pool tokens in this system, it's not like Uniswap where you have to withdraw both tokens simultaneously. You can withdraw any token, right, by itself, and that causes the price to change. And so, when we are looking at these arbitrage steps, we assumed that the overall pool size had to remain the same, but that assumption isn't necessarily true. We can balance this pool by changing its liquidity levels. So it is I think worthwhile to assume that maybe you are the only LP in this pool, and rather than let someone arbitrage against you, instead you're just going to withdraw liquidity from some of these units. And what would that look like? Another one, so this one I think is maybe slightly easier to answer than the third one, which is what if you're only allowed to mint pool tokens, right? Can you get the pool into a balanced state just by contributing tokens as liquidity to certain reserves and bringing it back up to that level? Now, the reason why these get slightly more difficult is that you can't use the equation that I gave you before, because that one assumes that the pool is staying, has a static size, and all we're doing is adjusting the levels. But there's still something in there that I think that you'll be able to gather from the equation itself that will help you answer some of these problems. And then the fourth one is, can you take some of these learnings and then turn them into a Python class that actually allows you to switch up between some of these methods? Because you could imagine that, especially if you are the administrator of a system, or maybe maybe a vault manager for a DAO's treasury or something, you might want to calculate what the most efficient path is for rebalancing a pool, including things like gas costs and stuff like that, or the likelihood of being front run or whatever. And so being able to have access both to swaps, liquidity provision, and removal functionality when you're rebalancing is something that is certainly worth the effort of studying. Okay, so today's lecture, concentrated prototypes. So we're going to be building very, very quickly on a lot of the bedrock that we have that we've laid out in the previous two lectures. And so I'll be revisiting some of the concepts as we go. But in general, I'm going to assume that you are very, very familiar, very very happy with everything that's been presented. And I'm going to move into more sort of a geometric intuition for what it even means to be a concentrated liquidity system. So you'll remember that these formulas are the ones on the left that appeared in the Bancor's original patent, and I swapped these out for the modern convention. I'm now going to show you Bancor's second patent, which was published in 2020, and it looks very, very different. So this is literally the text of the document, and the way that virtually amplified liquidity is presented is like this. And again, this is because you have to remember that in its time, there was no default way of describing these things, right? When you're the first through the gate and sort of establishing the syntax and nomenclature for the first time, it's not always immediately clear how certain concepts should be presented or represented. So here we've got, just a quick blurb that talks about virtually amplified token balances. It says that these are the formulas that are used to achieve it. And then underneath, it talks about what each one of these objects actually means. And some of these descriptions, again, are a little bit, I think they're a little bit lacking in detail. If I was to, give you just the text on this, on these two slides, I think you might be able to get to, a fairly good working understanding of what it actually is, but without the context of the rest of the patent, I think it would be probably impossible. So I'm going to start with what these concepts actually are, and then we're going to build back up to what is presented in those formulas that I just showed you. So this is the key, right? In Bancor V1, there's essentially a 1 out the front here in terms of the invariant function. Whereas in Bancor V2, rather than forcing this to be 1, you can make this any number, any real number. And that means that you are essentially virtualizing a different liquidity pool. So if you've got a certain number of tokens that's fulfilling the Bancor V1 bonding curve structure, when you move into the V2 prototype, this number A then moves the bonding curve to a different position. And this has some interesting effects. So first, let's go through what this transformation is and what it means. Two of those variables that were defined in the document that I just showed you were called the primary stake balance and the secondary stake balance. And what this means is it's the number of tokens that were available at the moment of the pool's creation, right? It's literally the tokens that were staked when the pool was made. And I'm just going to denominate these as X sub 0 and Y sub 0, just for this demonstration. Now, remember, if we're in the V1 context, we know precisely what the marginal exchange rate is between these two tokens here, right? Or if you like, just what the first derivative of that bonding curve is. And I do encourage you, if you haven't already, to derive this for yourself. But it's essentially it's always going to be negative y0 over x0 in this particular case, multiplied by the reciprocal of their reserve weights, of the ratio of their reserve weights. And so in this particular case, let's just say that this is a 50-50 pool, because it doesn't matter too much, but it's familiar enough that we can work with it. This means that there's a point on the V1 curve and on the V2 curve that have that same derivative, that have that same slope. And so we're just going to mark those out, okay? So just to recap, we've got the normal bonding curve here, and we've created it with some initial set of tokens. Imagine if you're setting up a Uniswap V2 pool, for example, you might provide 2,000 USDC and 1 ETH to it, right? Then that would mean that if your ETH is your X, then this would be 1, and Y would be 2,000 or something like that. Or maybe you're creating a stable coin pool, right? And you're only putting USDC and USDT in it. They're both coming in equal proportions, maybe 1 million of each. Then Y0 and X0 are both 1 million. And that means that we can measure the first marginal exchange rate at the time that the pool is created, right? On that first block. And all I'm doing then is saying, okay, now that I've got that tangent line to this curve, then I need to draw a parallel line to that line that is also tangent to this next bonding curve, right? So you're looking for that kissing point, the thing that kind of translates between these two curves. Now, after that, what you'll find is that point is whatever the x0 and y0 variables are, multiplied by this coefficient a. Now, it's worth asking, if we are pretending, right, if we're virtualizing this second bonding curve, then it's only got the same number of tokens that the first bonding curve has, but it's now, it's now using them at a faster rate. And so whatever that initial amount was, we can subtract it from where we've ended up on this virtual curve, to find the point on this curve where we run out of that token, right? So again, if we started with Y0 tokens, let's pretend this is USDT. We are amplifying that reserve amount by some coefficient A, but we're only virtualizing it at that stage, which means that even though it's only got Y0 tokens, it is behaving as though it has A times Y0 tokens. And doesn't mean that you got more tokens. So by the time, that's when it's actually run out. And the same is true in the other dimension. This means that if we, by the time we're running out of whatever this Y0 token is, we're also going to be finding the maximum amount of whatever the x-axis can afford. Okay, so same pattern over here. We're going to take whatever x0 is, and we're going to subtract that from the amplified balance to find this point where it runs out of that token. And then we can infer that if we are at this position on the curve, then we are at some maximum amount of Y tokens. And this is kind of almost everything you need to complete the geometric construction that I'm trying to show you. Before we complete it, though, we need to revisit these tangent lines at these different points. So you'll remember here, we started at the point Y0, X0, and we drew a tangent line to the curve there. And then we made a parallel line and asked the question, where does it kiss this other hyperbola, this larger hyperbola? And we said that that's at AX0, AY0, which is convenient. What we want to do now is we want to ask the question, first of all, what is the derivative of this larger hyperbola at the point where we're running out of tokens, because this is essentially going to tell you what the marginal rate is at the very edge of what your virtualized token balances are going to be able to service. So all I'm doing is tilting these parallel lines over, and I'm doing it to the point where we are now tangent to the hyperbola on V2. And then I'm looking at where does it kiss the original V1 curve, okay? And then we do the same thing for the other set of coordinates. So here, this point, all the way up here, this is when we've completely run out of whatever the X token is in terms of real tokens. And we're at our maximum balance of Y tokens. And down here, we're looking at whatever we're looking at the point where we've completely run out of Y tokens, and we're at some maximum amount of X tokens. And then we're just taking the derivative of the curve at exactly those points, and then drawing a parallel line back to the original curve, the unamplified curve, and marking those positions that it kisses as well. And what this results in is the construction of two squares. And the way to understand this A term, this A coefficient, is that it is the square root of the ratio of those two areas. That is the actual definition, the geometric intuition that I want you to have for what it means to have this A coefficient. Okay, so what does this mean? Like, what is the significance of this? Why even have A? Why is this a helpful way of defining a concentrated liquidity curve? This is the best intuition that I think I can give you, is that if we think about how many tokens can you trade between this point on the regular bonding curve and the final point, and you think about how many tokens you can trade across those same price points on the concentrated derivative, what you'll find is that the ratios of those two trades are exactly the same, right? Meaning that, whatever I'm swapping on that tiny V1 box and whatever I'm getting out so my swap is in the X direction and I'm pulling out Y. So the ratio of this amount to this amount is the same as the ratio of this amount to this amount, which means that effectively the execution price for these two trades is the same. However, their magnitudes are obviously very different. And this is the key, right? And maybe if you've been around the bonding curve space for a while, you would have heard, terms that I hate, things like capital efficiency, and maybe I'll go on a rant at some stage about why it's the wrong word to use. But the point is that you are getting a better slippage profile for the liquidity that exists at the cost of no longer being able to offer liquidity at every single price point, right? You are now bounded between two prices where you can offer liquidity, and people that are interacting with that liquidity enjoy the benefit of better pricing. They effectively get cheaper prices trading with you. But if their appetite in one direction overwhelms the liquidity that pool has, it will simply stop trading because it's running out of tokens. The best, the best way that you can if you wanted to explore, what the thinking was like back then when this concept was relatively new, the Medium article for the Bancor V2 release is still up. Obviously, this is a deprecated system now for all kinds of reasons, and maybe that's something that we'll talk about in the next lecture. But if you move about halfway through the article, you'll see that one of the features, the one that we've just discussed, is that there is a change to the bonding curve in order to reduce the slippage. And that was motivated by what was perceived at the time to be very harsh criticisms against AMMs, because it requires a very large quantity of tokens in order to allow even moderate levels of trading volume. So this augmentation, this amplification or concentration of liquidity was the answer to that. And so just as an aside here, the term that Bancor used to describe the system was amplified liquidity. And when Uniswap, used the same idea 2 years later, or a year and a half later, they called it concentrated liquidity, which sound like they're kind of different things. Like when I think of something being amplified, I think about it getting larger, and concentrated, I feel like something getting compressed. But they are referring to exactly the same thing. These aren't opposite effects. Okay, so let's return to these equations as they were presented in the V2 pattern. What we're really saying here is that the current balance times, or the amplified version of the current balance, if you like, the virtually amplified token balance, where you are currently on whatever the bonding curve is equal to this amplification term times the original balance of tokens that you had at the time that the pool was created, if you want to think of it that way. I still think this is the best heuristic, minus that same value, whatever that stake balance is, minus whatever the current balance is. So this would be like a variable that you store in the contract that would sort of orient, it kind of marks the coordinates of whatever bonding curve you started with and say, like, this is the place that we're currently amplifying. Now, of course, this isn't the best way to, I think, present this equation. We can very easily just multiply out that negation and then, gather like terms. We end up with something that I think is a little bit more presentable. But these are exactly the same meaning as what these code excerpts we're trying to present. And then, of course, once we're there, all it's saying is that everything else from here on out is the same so long as we don't run out of tokens, right? So this is that same V1 bonding curve invariant that you're already very familiar with. It's just that now, instead of using the X balance directly, it's now X tilde, where tilde is telling you that this is a virtualized system. The bonding curve is much larger than it should be, meaning that it can run out of tokens at any time. Okay, so we don't have to stop there. This is a very inconvenient way, I think, of handling this type of system. For the record, though, I think Kyberswap's DMM, it actually uses that implementation exactly as written in this pattern. They still maintain balances both of real tokens and of virtual tokens, and include variables in the smart contracts as to what the price will be when it's running out of tokens and that kind of thing. But I think a slightly more elegant approach is to, rather than have the some pretend virtual token balance up somewhere else in this curve, is instead force the place where you're running out of tokens to be commensurate with the Cartesian plane that you're actually using, right? So rather than say, oh, I'm running out of tokens up here at some virtual balance, you would rather just use the real token balance itself. And that means that you're just then, you need to get out of this equation. You can no longer treat it this way. And you just need to basically apply some sort of correction factor that moves you, from this amplified case down so that the point x0, y0 is commensurate with both the amplified and the unamplified bonding curves. Now, there are more than one way that you can approach this problem. And I have a demonstration. This is going to be very, very short. But there is just for acknowledgement's sake, there is a person somewhere in the world named Kevin. I don't know any more than that. But he's got a YouTube channel, GitHub. This is his Twitter. And he's created a whole bunch of really interesting material. He's got a game out on Steam, I think, where it's like it's just a free exploration world sort of thing. But instead of living in Euclidean space, you can start, you can move into spherical space, or you can move into like hyperbolic space and sort of get an idea for what those things might look like. And I suspect that this program that he created, that I found in his GitHub, was created specifically to deal with with some of the problems that you might encounter when you're creating a mixed perspective game like that. So you can just confirm for me that you see like a blue grid with 5 red points and a white circle.
Yeah, yeah.
Okay. So what this is a visual proof that any 5 points uniquely define a conic. So you can see I can move some of these points around, and it will start to draw like an ellipse. And it really, like a circle, it turns out, is just a very, special kind of ellipse. But then as I move some of these out, it will become a hyperbola, and then back into an ellipse. And so this is, I find, just a very visceral way of sort of coming to terms with what some of these things are. But the more you play with this, you realize that a parabola is just like a very special case of an ellipse, where the opposite vertex is at the point at infinity. And then when you start to pull these apart, you realize that a hyperbola is also just a special kind of ellipse, but where the opposite vertex is kind of past infinity. And so the point that I'm raising here is that if you know something about these 5 points, right? If you want to create a specific type of hyperbola, you only need 5 reference points, and you can then move this anywhere in the Cartesian plane and generate your hyperbolic bonding curve that way. The interesting thing is that all of these 5 points can also be replaced by tangent lines. So you don't even need just 5 points on the curve. You can actually just define 5 linear equations, and those will also uniquely define a specific hyperbola. And so this is, I think, key, right? This is just such a helpful thing when you're trying to do stuff in the bonding curve space, to know that essentially everything that you want to do can be expressed as a conic section, and that if you know 5 points or 5 lines or any combination thereof, that you can easily define a specific equation anywhere on the Cartesian axis that has the properties that you want. So, for example, one of these tangent lines could be the price at which you are running out of one of these tokens. Another one of these tangent lines could be the asymptote, right? Actually, it can't be the asymptote, but you understand what I mean. If you've got certain, if you know certain things, right? Coordinates where the bonding curve must pass through, or tangent lines, prices effectively that that it must adhere to, then you can easily create a formula for your conic section, and then just create that. Okay. Just as a quick aside, I also want to recommend this video by Tehran Knudsen, which has a look at the projective plane, which is, again, probably the best way to understand those conic sections that I was talking about before. And really, like, I wish I could say that I just watched these 2 videos and then came up with the equations that I'm about to show you, but that's not true. I kind of came to these videos in the process of trying to understand some of the things that I had created via other geometric and algebraic constructions. But I wish that I had started with an understanding of this geometric projection, because I think that would have been just a much more efficient way of doing stuff. Okay, so moving on. Just quickly, we're going to treat the reserve invariant the same with respect to how the reserve weights work. Okay, so just remember that this sentence in formal logic just means that for every reserve weight that we have in the set of reserve weights that define our bonding curve, they are all a number between 0 and 1, and the sum of all of the reserve weights is equal to 1. That is not changed. Everything else is going to change. This is now our invariant function. So let's just quickly have a look through this. The part on the right, I think, is relatively self-explanatory, right? This is literally that it just says that the product of all of these, remember, these are these reference points, essentially the balance of that token when you set up the bonding curve in the first place, or like when you created the liquidity pool in the first place. But that, again, that is just a way of thinking about it, a way to intuit through what that coordinate means. It doesn't have to start there, right? This could just be an arbitrary coordinate, and you can actually start your liquidity pool with some other balance of tokens from the outset, and move back to a situation where the real token balances are equal to some imagined starting state of the pool. So the point that I'm making here is that this is basically this x0 parameter. It is just another constant, right? It's just a parameter that describes your bonding curve. It is essentially the coordinates of these points, right, that lie somewhere on your bonding curve. So when we've got all of these together, let's say in n dimensions, they are all referring to one explicit point on the manifold that your hyperbola must pass through. And so we take the product of those, and that effectively becomes our C constant or our K constant. The other terms I don't think are too difficult to understand. XPK means what it did before, right? This is just the real token balance of our liquidity system. The difference is that it used to be the case where this number cannot be 0, right? It had to be a number greater than 0. But now we're in a concentrated liquidity case, and so now 0 is allowed for these token balances. And that's going to mean that some of the equations that we introduced in order to describe these systems become necessarily complicated as we have to handle, as we now have to handle zeros in the algebra. This x0 is the same one that's over here. So this is this constant is used on both sides of the equality. And then A is again that amplification term, which I showed you is if you draw boxes around the unamplified curve and the amplified curve at the prices where the amplified curve is running out of liquidity and compare the ratio of their square roots, you get this number A. The problem I have with this particular expression and the choice of A is that I would much rather have a system that I can denominate between some maximum amplification and some minimum amount of amplification. And the problem with that is that if I wanted to get to maximum amplification with A, I would need to literally take the limit all the time as A tends to infinity. But there's a much faster way that we can sort of shortcut around that, and that's to define a different parameter, gamma, and gamma is just the inverse of A. And then we can just substitute 1 over A for gamma through all of these equations, and now we've got something that is, I think, a little bit more compact. We have to, we don't have to deal with infinity as much. We still have to deal with 0, but you can see, sorry, hello? Sorry, I couldn't tell if someone was trying to say something. You can see that gamma equaling 0 here is just not a problem, right? Because it just means that it cancels out this term. And then we just end up with x0 is equal, the product of all of these x0 coordinates is equal to the product of all of these x0 coordinates. Not too difficult. Okay, so now that we actually have an expression that we can use, or an effective reserve invariant using real token balances. So there are no virtual token balances in this expression. Let's now think about what each one of these parameters actually does. So when we're dealing with gamma, what I want you to imagine is that you're sticking a pin in the kissing point between the unamplified curve and the amplified one. When we change the gamma parameter, what we're doing is effectively symmetric stretching of the two axes. And I'm going to show you this on Desmos in a minute. But just remember what I've said, right? When you're playing around with gamma, this particular point, in fact, this is the only point on the entire plot that will remain exactly the same on the amplified curve. And the relative scale of the X and Y axis is going to move. Okay, what about the reserve weights? For the reserve weights, just remember that they must sum to 1. And so in the case where we've only got 2 dimensions, either one of these is going to be, 1 minus the other. We still keep this point in the middle perfectly stationary. And now we can asymmetrically stretch these axes. So when we're compressing one axis, we're stretching the other and vice versa. Okay. What about when we're playing around with the x0 coordinate? If we're moving x0 or if we're changing the value of x0, what we do is we basically put a pin in the y-intercept for this curve. And then that allows us to just stretch or compress the x-axis. And then the opposite is going to be true of y0. If we're playing around with this parameter, we're effectively putting a pin in the x-intercept and then adjustably stretching or manipulating the y-axis. And in a way, that makes sense. So at the end of this demonstration, all I want you to remember is that y0 allows you to just stretch the y-axis or compress the y-axis. If you're dealing with x0, you are just stretching or compressing the x-axis. Gamma, you are stretching and compressing both axes together symmetrically. And when you're playing with the reserve weights, you're compressing and stretching them asymmetrically. And so, as I said, I think that this is going to be slightly easier to appreciate if we move to Desmos. Sean, can you confirm for me that you can see a Desmos graphing calculator screen?
Yeah, got it.
Perfect. Okay, so let's see if we can repeat some of those properties that I just said. So just confirm for yourself, right, that these are the expressions that I had up before. The thing you'll note here is that I'm using x0, y0 for the constant here. This isn't absolutely necessary, but it helps me to demonstrate for you that these curves are referring to the same sized curve. It's just that one of them is augmented compared to the other. So the first thing I'm going to show you is what happens when we move our x, okay? So you can see here, I've already set our y to be 1 minus this value so that these things will add up to 1. And you'll see that there is this kind of pivot point, right here, where if I move in one direction, the curve is kind of rolling around as if it's literally been pinned in place at that exact spot. But it's changing both the y-intercept and the x-intercept as I move it around. So that's the reserve weights sort of acting on this invariant function. Let's see if I'm going to put that at 220. So now watch what happens when I move gamma around. See how it's no longer rolling around, but it's like it's becoming more and more like the curve that we started with, or more and more like a straight line. And in fact, when gamma is equal to 0, it is in fact a perfectly straight line, and you would get what's called a constant sum bonding curve, and that's the limit of this invariant function as gamma approaches 0. And as gamma approaches 1, it's actually equal to just the same bonding curve that we started with. This is no amplification at all, which brings some interesting questions into view, which is what happens when we go past 1. Now we're getting not amplified liquidity, but contracted liquidity. This is now a liquidity pool that is behaving as though it's got less liquidity in it than it really does. So rather than using virtual token balances that are larger than the amount of tokens we have, we're now using virtual token balances that are smaller than the amount of tokens that we have. Another interesting question is, what happens when we let G be a negative number, right? What does it mean to have a negatively amplified liquidity pool? And this actually gives you something that we haven't seen before, which is a bonding curve that goes the opposite way. Now, this isn't, you might think at first that this is a ridiculous thing to have, right? Why would you want a bonding curve that has this feature? but actually this is a timeless Dutch auction, right? So this would give you essentially the more of the thing that you buy, the cheaper it gets. This is actually how most of the commodities in the world are sold, right? If you come to my supermarket and buy, a kilogram of potatoes, I might sell it to you for 50 cents a potato. But if you come to my factory and buy a ton of potatoes, I'll give it to you for 1 cent a potato. The more of the thing that you buy, the cheaper it is. And this is a bonding curve that expresses exactly that. I wouldn't call that a financial paradigm. I'd actually call that an economic paradigm, right? You are trying to incentivize someone to take more of your inventory. And so having a negative amplification actually gives you that. The more of the thing that you buy, the cheaper it gets, right? The exchange rate becomes more beneficial for the trader as they're taking inventory out of the system. Think of it like flash sales or something like that. And like I said, you can think of it as a time-independent Dutch auction. And it's worth pointing out that once we're here, we can still play around with RX, right? So we can tailor the how aggressive this curve actually is, right? So you can see here it's got a relatively consistent relatively consistent rate, but then towards the end it sells everything off relatively quickly and things like that. So this is how the reserve weights and gamma sort of affect this type of bonding curve. Now we can play around with x0 and y0. And I think in order to do this, I'm going to bring gamma back to 0.5, and I'll bring reserve weights back to half so that we can see things a little bit easier. So you can see here that the y-intercept of our augmented curve is now at 300, and the x-intercept is also at 300. But watch what happens when I start to play with x0 here. I can now move the x-intercept, but leave the y-intercept exactly where it is, right? So if I take this back, to about 1/3 of y0, you can now see that the bonding curve begins at a token balance of y equals 300, x equals 0, and continues throughout this profile to a token balance of x equals 100, y equals 0. And I can play around with both of these, right? So if I'm playing around with x0, I'm leaving the y-intercept in place, and I'm moving the x-intercept as I want. And if I'm playing with y0, I'm leaving the x-intercept in place, and I'm moving the y-intercept to wherever I want. And so you can see that with some combination of all of these things, right, you've got like what is effectively a very, very powerful equation, because all of these things will give you sort of like different bonding curves with different properties, including this Dutch auction style thing and whatever else. And I'll make sure that that I share this this calculator with you guys. I'll give the link to Rabbit, and he can distribute it or whatever. But yeah, I just wanted to make sure that this is as clear as possible, because it is, I think, this is really the fundamental theory of what it is to be a concentrated liquidity curve.
Okay. Mark, can I ask a quick question?
Of course.
I think it's a kind of silly question, but it's just how did you get the two curves touching at that point? If we consider the original amplification, we have a sort of, the second curve is shifted up and to the right. So what changed to get that curve, second curve amplified, but also tangent?
Yeah. So, and this is kind of what I meant when the best thing to say. Let's revisit those two slides. So what we have when we're looking at this amplified curve is just a virtual token balance, but we know that this number up here, right, is this amplification coefficient multiplied by whatever the remaining tokens is. In fact, if I come back to, let's go back a little bit farther. So let's have a look at what this is actually telling us. The equation says the primary column balance amplified is equal to the primary state balance amplified. And remember, I said that this primary state balance, this is just a coordinate. This is the x0 or y0, whatever it is, times that same amplification coefficient. But then we're still getting the primary state balance and the primary column balance in here. And the thing that I'm trying to show you here is that we don't actually care what the primary current balance amplified is. The things that we care about are all in here, right? So this x tilde is kind of irrelevant. All we need to know is how x tilde interfaces with everything else. So if you take this invariant function here and just replace it with these terms, right? So instead of using x tilde, use x0 a minus 1 plus x to the power of rx, right? And instead of using y tilde, use y0 a minus 1 plus y to the power of ry. And instead of using c, we're going to use x0 times y0, right? This is the thing that gives us that, that same point that you're talking about. And the reason is simple. If you imagine that the amplification coefficient is 1, right? Meaning there is no amplification. The virtual tokens is the same as the other tokens. Then it should be clear that whatever these two components are is equal to the normal constant of of the constant product Douglas-Cobb function that we've seen today, right? That we've seen in the last two lectures. So you start with some very basic, you can start with these very basic assumptions and construct the formula that way. Or you can start from the projective plane and develop the equations that way. They both arrive at exactly the same solution. It's just that in one of them, you're basically just arriving at the same conclusion from two different perspectives. You are either deliberately creating a hyperbola with certain properties, like an asymptote at certain sections, x and y intercepts at certain sections, and then you're just drawing that, and you can, after a lot of algebraic manipulation, arrive at an answer. Or you can say, I'm creating an amplified curve, but I don't care about my virtual token balances. I only care about my real balances. And both of those solutions converge at a set of equations, including the two that I've shown you today. Does that help?
Yeah, that helps a lot. Thank you.
Perfect. Okay. So I have now an animation that I prepared using Manim that I would like to show you. I hope this plays smoothly. If it's too jerky, let me know and we can move on. But this is a software package for Python and Cairo that was created by Grant Sanderson of a YouTube channel called 3 Blue 1 Brown. And what I'm doing here is this is one of the other equations, by the way, that you can use to describe this amplification. But the reason I've made this is because we can now start exploring it in logarithmic space under certain constraints, whereas on Desmos you can't do that, or at least not very easily. So let's have a look at what we're doing here. What I'm showing is that when gamma is equal to 0, you are a straight line, right? The amplification is infinite, right? It has no slippage anywhere on its curve. And when we're at gamma equals 1, we're equal to the same curve, which means that any value for gamma between 0 and 1 is representing some arbitrary amplification level. And as we move x0 and y0 around, where y0 here is just k divided by x0, what we're doing is we're changing the point at which these two, where the amplified and the unamplified curves kiss, right? And so if we move k up and down, you can see that we get the same, the same effect that we would expect from a traditional bonding curve. So again, as we move gamma now to values higher than 1, we get contracted bonding curves. But everything else that I've said up until now still remains true. You can see here as I move x0 around, all I'm doing is changing the point at which the amplified, or in this case, contracted curve is touching the other curve. And then when we move to negative gamma values, we're effectively taking the mirrored version of this thing. But again, for the value of repetition, as I move that x0 coordinate up and down, you can see that the flipped curve is just sliding around on the original curve at exactly 1 point. And that 1 point, by the way, will have exactly the same gradient in both the amplified and the unamplified one. So there's lots of really interesting geometric and algebraic stuff that we can do here. Can you guys still see my screen, by the way?
Yeah, back to Desmos.
Back to Desmos? Here we go.
Yeah.
Sorry, my that animation killed my computer for some reason. Okay. So let's move on with other graphical representations, because so far, everything that we've done has been in 2 dimensions. But as I said, we spent the last 2 lectures building up to this case where everything that you do in 2 dimensions can be done in any number of dimensions. It's just it's just a manifold system. And so what looks like a curve in 2 dimensions becomes a surface in 3 dimensions, and then a hypersurface in 4 dimensions, or a volume in 4 dimensions, and so on. This again is a cross-eyed stereogram. You remember I presented one of these last week. And so if you go cross-eyed and let your sort of left eye focus on the right image and your right eye focus on the left image, you should get the illusion of depth here. I've noticed that some people can't do this. It's also contingent on the size of your screen and sort of your distance from it and that sort of thing to make the illusion effective. And so we also use these kinds of interactive plots and other things in order to achieve in order to get our bearings in how these systems actually look. And so what I will do now is we will go to Jupyter. Confirm for me that you can see this. Okay. So what I have here is a class that handles all of the generalized amplification. So all of the things that we've spoken about today and more. And so just go through this. The X underscore is a dictionary where each one of the keys is effectively the thing that you would put at that after that underscore to denominate the type of token that it is. So if we wanted to, instead of A and B and things, these could be like ETH and BTC or whatever. And I'm just starting them out with a certain number of tokens to get started. For those who aren't familiar, I'm using the decimal object here, which means that we can perform calculations with arbitrary precision. So there's a command that you can tell Python to say, I want to use 1,000 decimal places of precision, please, or 1 million decimal places of precision. And the decimal package is just extremely helpful for that. It's not the only one that allows for it, but it's the one that I'm the most accustomed to. The R's are obviously the reserve weights. X0, right? A, B, C, D, and so on. These are, of course, the coordinates, right? The point on the curve that we are trying to amplify. And I still think that is the best way to understand it. And then P underscore is the oracle prices, right? That we want to give to this thing. And then gamma is gamma, right? This is our amplification coefficient, or the inverse of our amplification coefficient. So if if we're feeding this a gamma value of 1/2, then that means that we're getting an amplification of 2x. And then we just create the class like this, and it's going to show us what these reserve balances are and everything else. So there are 2 things that I want to draw your attention to here immediately, which is this intercept column and this asymptote column. So watch what happens when I set gamma to 1. We get the intercept at infinity and the asymptote at 0. Now that should sound very familiar, right? When we're dealing with constant product curves, we kind of define them as being curves that have an intercept at infinity, meaning you can never run out of that token, and an asymptote at 0, meaning it's impossible to drive any token balance to 0. But when we change this gamma value to any number, let's say to 0.5, we're actually moving the intercept and the asymptote around. And this is, again, coming back to that projective geometry definition that I was trying to get you to entertain when it comes to conic sections. These are now variables that we can use if we wanted to define our hyperbola, and they are redundant with this x0 term. So if you were so inclined, and you thought, this staked balance or origin balance or x0 parameter is something that you find unhelpful or is unappealing for any reason, is irrelevant for your implementation or the product that you're trying to build. What I'm showing you here is that you actually have the freedom to choose from a large number of other variable types that will define exactly the same hyperbola, but under different, like from a different perspective. Like there are a very large number of redundant ways that you can write an equation for exactly the same conic, which is, I think, both a surprising and beautiful realization to come to, because when you are, trying to create these systems, especially in a smart contract sense, you will have limitations such as storage space, such as precision in a fixed point infrastructure and other things that are going to influence how you decide on which equation is worth implementing. And so to know that you have this enormous over parameterization space to explore to arrive at the exact implementation that is the most gas efficient, that is the most numerically stable, that is the fastest to compute, these kinds of things are things that as a bonding curve research group, you should be aware of, because just because you can create a function that has the properties that you want doesn't necessarily mean you're going to be able to implement that function on a blockchain. There are constraints. You need to we're engineers in a way. You need to work under the the limitations that the system that you're building for provides you with. You can't sort of impose your demands on the system. You have to work with what you're given. And so these intercepts and asymptotes are is just another part of that parameter space. And I've got a homework question about these things coming up. So just know that when we get there, that I've given it the appropriate amount of foreshadowing. The oracle price means the same thing as it did in the last lecture. And I can show you what happens when we rebalance this pool, is that it actually tells me what swaps to perform in order to get the pool into that state. Now, what's interesting about this one is that you all saw what at the beginning of this lecture, the answer to the homework question from the last lecture, which was, here's a formula and we can find the coordinates at some point, and then even though I didn't show you how to generate this method, I'm sure many of you thought, and I know that at least Rabbit and Octopus were thinking, that they have a way to approach, an algorithmic way to approach that problem that they think that they could arrive at relatively simply. And maybe that's true. But now think, what would that look like in an amplified scenario, right? If you're using a concentrated liquidity version of an n-dimensional bonding curve, then you're going to need to start thinking about what it means to run into zeros or negative token balances, because we can't allow the bonding curve to ever approach a negative token balance. But that doesn't necessarily mean that that as it's running off of the curve, that it won't have an impact on how the price is quoted for the other assets. Something to consider. So for example, if I change the oracle prices here and rebalance the pool that way, you can see that now one of these token balances has actually run to 0. And this has, this has changed the way that these reserve weights are going to work in the other instances, and also means that that we now lose the ability to correctly quote the the exchange rate of A versus these other tokens, right? We can do it in one direction. We can still say, if you want to trade, B for A, it's going to cost you 1 point. Oh, sorry, if you want to trade A for B, it will cost you this number of A tokens per B token, right? If you want to buy one of these B tokens, the amount of A that you need to provide is 0.74. But unfortunately, you can't trade the other direction because it doesn't have any A tokens left to give, which is something that you need to consider. Because it means that these oracle prices will no longer refer to a specific point in 3 dimensions, but more it will only refer to a specific point in any number of dimensions if that point exists. If something has moved out of range, right, and this is the language that you will hear people discuss when they're talking about things like Uniswap V3, right? If the price is out of range, you end up all in one token in a 2-dimensional system. But what does that look like in 3 dimensions, in 4 dimensions, in 5 dimensions? Something to consider. And again, just for the sake of clarity, here, this is a similar plot to the one that I presented, I think, last week. But instead of, and let's just revisit the one that I presented last week. Comment. Come back to that one. All right, we'll look at that one in a minute. But we had this shape, or I presented this shape that looked like, here it is. Right? You guys remember this? We've got sort of the familiar bonding curve shape at the top, on the left, and on the right. Think about, if this is a 3-dimensional slice, that means that we're going to take the amplified curve that we're looking at is going to be a box, right, drawn around some coordinate inside this thing, right? And so what you need to be asking yourself is, what would this surface look like if, if I took like a 3-dimensional, if I took a cube and sort of moved it through the manifold, right? How would the part of this bonding curve that's inside of that cube, what would it look like? And it might not take you very long to convince yourself that this is the shape that it would have, right? This is literally that cuboid slice of the unamplified curve, okay? And we should also start thinking, what else can we do with this? Because this is still looking at, I think, a case where we've got an amplification of, let's restart this, of 0.5. Well, what would it look like if we increased that amount of amplification? What if we went to like 0.2, 0.2 to start? Oops. See, now we get sort of what looks to be a much flatter, a much wider surface area. And in a way that should be intuitive, because when we're going to larger amplifications, we're effectively, drawing a smaller and smaller cube that we're using to pass through that manifold. And so, you can still see that we get that curvature, right? If we zoom up on this, if we zoom up on this a little bit more, you can still see that we have this gentle curve in each one of these axes, right? From the top, you can see there is that part of the bonding curve. And on this dimension, there's that part of the bonding curve. But what do you think it would look like if we increased the if we increase the amplification to infinity? Just quietly think to yourself, like, what would that actually be? Let's just run all the cells again. Right? We now just get a triangle, right? A perfectly straight triangle. And this in a way should make sense because this is something that is slipping, like where the price is slipping at a rate of 0. So no matter where we move on this surface, the gradient in every dimension is still the same. And we don't even, we're not just limited to A, B, and C. We can, move through these dimensions the same way that we have before. The point is that the exchange rate will always be the same no matter where we are. And so this would be appropriate for something like a stablecoin pool, where you can have like USDC, USDT, DAI in there, and just set the amplification to infinity. And this will always give you a one-to-one, if you so desire it, a one-to-one rate of exchange, regardless of whatever the balances currently are. Okay. So coming up on 80 minutes, which is good. So I've timed this well. Okay, so the real take-home message that I think I want you to take away from this presentation is that with the V2 invention, what we really were trying to do was to offer a system that for the same liquidity amount offered better transaction rates for people that are interacting with that liquidity. And so the way that it was, it was conventionally explained was to just imagine a larger liquidity curve than was actually there by multiplying essentially all of the reserve balances by a certain number in order to achieve a liquidity, like a new amount of virtual liquidity. And after that, everything is the same that you've seen before, right? Apart from this equation, which is new, this, this reserve invariant and this sum of the reserve weights and this coordinate of I given J, etc. These are all like directly out of V1, right? And this is why I've copied it across. So you can actually compare these, right? Apart from the tilde, this equation is the same. This equation is literally the same. And again, this equation is the same apart from the tildes. But if you want to use the true reserve invariant, meaning what is the actual, if you want to track, the actual token balances inside the pool, not on some imaginary amplified pool, then you need to actually move the hyperbola around and define where its intercepts are on the y and the x-axis. And if you're in a large number of dimensions, then you need to define where its intercepts are on every single one of those dimensions. And when you're changing those intercepts, be aware that you're also changing their asymptotes. And these two things will have, are linked together in some very profound way. And it's a little out of the scope of these presentations, but if you find yourself exploring some of these ideas, and you feel like reaching out to me so that we can go over them together, I'd be very happy to entertain that. But yeah, it's something that I think is best done. It's best discovered on your own, right? To ask the question, what is the relationship between the intercept of a augmented or an amplified hyperbola and its asymptote? Or what is the relationship between the ratio of those two things and the amplification coefficient that I'm using? All of these things have a very strict algebraic set of like effective laws that define the conic, and so that that can't be that can't be violated without effectively drawing some other shape. Now, this is where things get tricky, because that coordinate of I given J function has a gamma term in a denominator, and I've already shown you that we are more than capable of using gamma is equal to 0, which means that for a lot of these expressions, you're going to have to get very familiar with taking the limit, and some of those limits are very untrivial. So in this particular case, it's not too bad. So the limit of this expression as gamma approaches 0 is this, which, I know that these things look dramatically different, but I think that you should be able to prove to yourself that, because gamma is equal to 0, a lot of these things kind of cancel out in some helpful way. There's a very large number of methods that you can use to find these limits. I'm also going to give you these token swap equations just to save you a bit of time. And I think it is kind of that there's some level of appeal in the way that these are presented, because they do look, it's obvious that they come from like the same family of geometry as the original swap equations that you've seen, right? So you can see here that there's some term out the front that is referring to the token balance of the thing that you're trying to swap. And then you can see that inside the parentheses, you still have 1 minus some term, which is like the ratio or some expression of the ratio of those token balances and their amplification levels. So the overall skeleton, I think, of the swap equation remains the same in this one, whereas in a lot of the other algebraic representations of this same theory, the swap equations can look, it can look extremely alien with respect to each other. So I think that this is the best place to start, because at least you can get some like visceral understanding for what the similarities are between these two systems. But then later on in the fourth lecture, I will show you much more exotic representations of these things that are much, much smaller, much more computationally efficient. But again, we've got gamma here in the denominator, meaning that we need to take the limit if we're using gamma is equal to 0. And look what happens. This is telling you that this is actually a variation of the constant sum or the constant price swap equation, because x0j and x0i are just constants, and so is rj and ri. So this whole thing over here is just constant. And so what this is telling you is that the swap of xj for xi is just whatever whatever your input is multiplied by some constant. And then if you flip this upside down, you get the result in the other direction. And so this is, again, just a nice, it shouldn't be surprising, because we just saw graphically that when you take gamma to 0, you end up with a perfectly straight line, which is the invariant representation of a constant price formula. But now we're getting it from a different perspective as well. And it's just nice to get that confirmation. Similarly, the marginal price formula, again, very, very similar construction to what you've seen in the unamplified case, which I think is, again, in terms of your visceral understanding, is going to support a much deeper understanding of these equations before we get into the more exotic archetypes. And then if you take the limit of this, if you take the limit of this, both as the swap amount is approaching 0, and as gamma is going to 0, so infinite amplification, again, you can see it approaches some constant, meaning that as the amplification reaches infinity, we are approaching a situation where the marginal rate of exchange is constant no matter where you are, which is, again, another way of defining the constant sum or the constant price bonding curve, like M stable used, for example. So now we're coming up to, this is the end of the lecture. And I want to issue a little bit more homework this time than on the last two, because I think there's a lot to digest here. The first, these kind of go in ascending order of difficulty, where the last one is especially challenging. So the first one is just to show that for any finite amplification factor, that the asymptote for any dimension is equal to whatever this x0 coordinate is for that same token, multiplied by gamma minus 1 over gamma. And you'll note here that as long as gamma is a number between 0 and 1, excuse me, as long as gamma is a number between 0 and 1, this means that the asymptote is always going to be negative, which makes sense, because when we're amplifying these curves, we're really pulling the asymptotes away from zero back into the negative domain. And when gamma is a number greater than 1, the asymptote is going to be a number greater than 0. And again, that makes sense because you saw that we're also able to contract the curve, which effectively moves the asymptotes back up off of the origin and and into the positive domain. So I want you to show that this is true. And then, of course, after you've done that, show that for an infinite amplification factor, that the asymptote doesn't exist, right? Essentially, it becomes negative infinity. Now, the reason I've said that this is negative infinity rather than doesn't exist is because I'm referring back to this geometric projection where the points have it, and this could be plus minus infinity, I suppose. But the idea is that it's actually there. It's that straight line is still a type of conic. It's just a it's just a very special one. Okay. The next set is to then deal with the intercepts. So show that for any finite amplification factor, meaning gamma is not equal to 0 and the A is not equal to infinity, show that the maximum possible true balance of any token is this x-intercept. And this will, like I said, we're going slightly more challenging. But this is basically showing you, imagine you've got an amplified pool, let's say with 5 different assets in it, and one of those assets goes to 0, right? Goes to a price of 0. So that the market effectively dumps all of that token and it goes down in value 99.9999%, right? Something like Iron Finance or, UST or something like that. That means that, the market, when it's equilibrating your pool, is going to be dumping all of those tokens into it and removing all of the other tokens, meaning that eventually your liquidity pool will be composed of nothing but that one token. That'll be the only token left. And the question is, for any arbitrary liquidity pool, how many of those tokens will you have if its price goes to 0? Similarly, for an infinite amplification, so when gamma is equal to 0, when A is equal to infinity, show that the limit of this expression is actually just the x0 constant divided by the reserve ratio. And last but not least, I need to refer back to some of the conventions that I introduced in the last lecture, which is that for these price values, that they're all a number greater than 0, and that I define it to be in this direction, right? It's the token divided by the US dollar value, or by its euros value or pesos value, it doesn't really matter. And we do that so that when we take the ratio of these two prices, we end up with the marginal price formula. So for example, if we're taking P ETH over P BTC, we'll end up with 10 ETH over 1 BTC, which matches up with the way that we've defined the marginal price. I showed you at the end of last lecture that there is a way that we can take all of those prices and compute all of the coordinates for all of the tokens, no matter the number of dimensions, which is an extremely helpful thing to have because it's how we performed arbitrage when we were running these things. And I've showed you during this lecture that the class that I have in Python can do this on a liquidity pool that has an arbitrary amplification level. And so this is the question. I want you to show that for any X balance, where that X balance is 0, that the highest possible price for that token is equal to this expression. And for that same token, where that token's balance is equal to its intercept, that the minimum possible price is equal to this expression. This is extremely difficult. And this is I'm giving you the equation. So you've got the light at the end of the tunnel. And so you've actually got all of the information that you would need if you wanted to create, for example, a class method to perform arbitrage. but that's not going to make you any smarter, right? I give these equations out to people all the time, and they'll never build a protocol. The question is, how did I get to this answer? And it's a long path, or at least the way that I did it was a long path. I know that that there are some among you who are exceptionally well versed in mathematics, and you may be able to get there relatively quickly. But the challenge is to get to the answer, not to know what the answer is. And then, last but not least, how should LP token issuance and redemption be handled in the system? Right? There is, I put this one last, suggesting that it's the most challenging because there's no right answer. There is just, it really comes down to what do you think the purpose of your protocol is. In terms of financially, I have a view of what the fair token issuance is and token redemption policy should be. But it's something to think about. And I think as a bonding curve research group and the kind of work that you guys do with, finding non-financial, applications for bonding curves and things, this is, I think, the kind of question that would be much better suited to like an essay, right? Something where the actual, the intent of the protocol and its builder becomes a part of the policy of how the LP tokens are issued and so forth. So in a way, I think that this is the most challenging, not because it's mathematically challenging, but because it really comes back to what is the philosophy and motivation of the protocol. And so very, very, very difficult indeed. Okay, and that brings us to the end of concentrated liquidity. The next lecture is going to be exotic bonding curve types. I will be revisiting some of the concentrated liquidity concepts that we presented in this lecture, particularly how it relates to, so we will derive the Uniswap V3 swap equation from the stuff that I presented today. I'm also going to derive the carbon equations, which for those of you who are unfamiliar with the protocol that we've released this year, carbon is an asymmetric bonding curve system where it has aspects of concentrated liquidity in it, but it is a one-dimensional trading system. So it's the only bonding curve I think ever ever deployed at least in a financial sense, where the rate of exchange is dependent only on the token's own balance. There is no reference to another token. And from that position, you realize that you've got like the smallest indivisible component of a bonding curve, and you can assemble that into sort of n numbers of dimensions and things like that. So we will be going over those concentrated liquidity examples, and I'm going to try and do that relatively quickly. And then we're going to be looking at the solidly stable swap, the curve V1 in stable swap invariant, and then also my own approximation, or let's say, I don't know, contender to these paradigms, and we'll look at what their properties are. I'm going to try and make the lecture 4 a little bit hopefully not as long as the previous 3 have been, out of respect for everyone's time, and also a little bit more a little bit more hands-on. I'm going to try and I haven't decided how I'm going to do it yet, but I'm trying to think of a way that we can sort of all share our screens, or use Desmos together or something. It's probably sort of overreaching, and maybe I'll just settle for a lecture like the ones that I've given before, but I don't know, maybe we'll follow it up with a workshop or something like that. Anyway, thank you all for your time. I hope that you found that beneficial, and I'd be very happy to accept any questions.
Bye.